Okay, so in today's videos, we're going to be talking about spontaneous emission. And that's another process that you could have when there's an atom or a molecule and it's in some state that's not the ground state. And this is a process that can happen even if there's no electromagnetic radiation around. So even if you just have an atom or molecule all by itself, not interacting with anything, what can happen is that that atom can make a transition down to a lower energy state. And then where does the energy go? Well, it gets emitted in the form of electromagnetic radiation or a photon if we're thinking about that quantum mechanically. Okay, so the picture is here's some here's some atom. Maybe it's a hydrogen atom, and this is one of the crazy orbitals that are not the ground state. And we just have that sit there for a while. And then after a while, what can happen is it all of a sudden emits a photon. And then after the atom is in some lower energy state. And so in terms of the energy levels, that would be, say, dropping down from that higher energy level to the lower energy level, or it could even drop down more than one level. Excuse me. Um, and so it's called spontaneous emission because it is not caused by any background electromagnetic radiation. So it's different from the stimulated emission where the background radiation is causing the transition from the higher state to the lower state. Okay, so you might be confused at this point because we're thinking about some state, and let's say we're talking about the hydrogen atom, and we're saying that this state initially is in some energy eigenstate, which is not the ground state. So maybe one of these NLM states. And we said previously, the way we understand energy eigenstates is that they do not evolve with time. When you have an energy eigenstate, all of the physical properties of the state are constant in time, and that's why we call them stationary states. And so now I'm saying that that energy eigenstate can make a decay and it can change to some lower energy state and emit this electromagnetic radiation. Okay, so what's going on? Well, the point is that in the real world, that atom is not just described by the hydrogen atom Hamiltonian. In the real world, that physical system of the proton and the electron, it's actually part of a larger physical system which includes these electromagnetic fields. So the full Hamiltonian would be the hydrogen atom Hamiltonian and a term which describes the quantum mechanics of the electric and magnetic fields. And now in our initial configuration, we don't have any electromagnetic fields turned on. We can say that we can think of the electric and magnetic fields as being like in their ground state. But the point is that in this combined system of hydrogen atom plus electromagnetic fields, the ground state of hydrogen and having no electromagnetic fields, that's a true energy eigenstate of the full system. But the excited state of hydrogen combined with having no electromagnetic fields, that's actually not a true energy eigenstate. It's an approximate energy eigenstate, but in reality, it's some combination of the energy eigenstates of the full system, and that means that it can evolve with time. And the way that it evolves with time is that for a while, it looks like it's just the hydrogen atom in that excited state with no electromagnetic radiation. But then the longer we wait, the, the state eventually is a superposition of maybe that initial state with no radiation plus some parts where the state of the hydrogen atom has made a transition and now we have some radiation. And so that's how we kind of understand spontaneous emission. And quantitatively, what we're going to want to derive is the rate for spontaneous emission. And that's often denoted by the letter A. And what that is, it's just the probability per unit time that your atom has made a transition from some state, let's call it A, to some lower energy state B. Okay, so that's only going to happen spontaneously if EB is less than EA. So that's kind of our goal for the videos today. It turns out that in order to understand that, we will need to take a detour and think about physics at finite temperature. So that's the subject of the next video.